Hi everyone, my name is Gericke, and this is my presentation for BlueSciCon. Myco materials Ganoderma Sessile, and how it can contribute to advancing sustainable scientific research. What is Ganoderma Sessile? Ganoderma Sessile is a species of polypore fungus. Polypore meaning that the spores, aka the cells of the fungus, are discharged through the gills of the mushroom. These are primarily found in eastern North America. The main parts of a mushroom are the cap, which is the top part that protects the mushroom, the gills, which are tiny pores underneath the cap of the mushroom, the stem, which supports and elevates the cap for pore dispersal, and mycelium. The mycelium, which is the root-like structure of the fungus that absorbs nutrients and water, allowing for the growth of the fungus, is the focus of my group's research. So this is how to grow mycelium. You have to cut the mushroom open and collect a live, clean sample of the inside tissue of the mushroom. Then transfer the tissue to an agar plate and seal it. Allow it to incubate 72 to 80 degrees Fahrenheit in dark or indirect light, and let it grow. It takes a couple of days for signs of growth, but a few weeks for full growth. You can add a substrate in order to use the mycelium as a medium for molding, which is what we will be doing. First, this is how to primarily add a substrate to the mycelium. You need to hydrate the substrate. In this case, my group used 171.1 grams of wood pellets. Then they mixed in 324.5 grams of deionized water and let them sit for 15 to 30 minutes, occasionally stirring. Add in 88.5 of less than 3 millimeters of wheat bran and 5.9 grams of calcium buffer until mixture is evenly mixed and damp. Flatten the mix into a heat-safe bag lightly, since the mycelium needs some air. Sterilize the mix by submerging the bag in water, about 150 to 175 degrees Fahrenheit, for 1 to 2 hours, then let it cool. Add the mycelium to the mix and mix evenly. Place the mix in a jar with holes in the lid. You need to place it in a dark and clean area with a room temperature of about 70 to 75 degrees Fahrenheit, and let it colonize for 2 to 3 weeks, making sure to check on it every couple of days. How are we using mycelium to make research more environmentally friendly? My group is working on ways to build a drone out of mycelium, completely replacing the need for plastic parts. We hope that these drones can be used for agricultural research, firefighting in hard-to-reach areas, as well as many other Earth observation-based research. We also hope to expand our research in the near future. And on the top left, you could see me making the mold for the drone, and I took out the parts of a drone, so the motor and the PCB board and the propellers, and I'm going to put it on top of the drone once it dries. How can we expand our research extraterrestrially? We know drones need an atmosphere in order to be able to fly, so we need to utilize a different type of drone that generates its own thrust to move around. These are called propulsion or hopping drones. Where does my research come into play? Propulsion drones generate a lot of pressure in order to be able to hop on surfaces such as the moons. The part of the propulsion drone that generates the most pressure is called the combustion chamber, which is the area where fuel and air mix together and are ignited to make a hot expanding gas that generates thrust. My research entails seeing how well mycelium works in high pressure situations. How will I be pressure testing the mycelium? In order to test how much pressure the mycelium can hold without cracking, I will have to make a hollowed-out shape and pump air into it. I've used the application AutoCAD in order to create a mold that will hold the mycelium. I'm going to make 2 half molds and put them together, allowing the mycelium to grow and form around them. This will create a hollowed-out shape. I will then add a bike pump nozzle into the shape, allowing the mycelium to grow around the nozzle. I will add air into the cracks, measuring the PSI, or pounds per square inch of pressure it held right before it cracked. This number will be considered the threshold for that sample of mycelium and can be used to compare thresholds for different thicknesses in the future. Making the mold for the mycelium. The first mold I made was a cylindrical shape just to get familiar with the application. Then I tried to make a mold that looked like a combustion chamber. However, to calculate the PSI of the mycelium, I thought it'd be best to start my research with a simple, more uniform shape. Therefore, I went with the sphere and added holes to make sure the mycelium was able to breathe. I created an insert to make sure the shape was truly uniform. Here are my results. The thickness of the mold's wall is 3 millimeters, and the radius of the sphere was 20 millimeters. The pressure test resulted in the sphere holding about 54 pounds per square inch without cracking. Therefore, we can conclude that mycelium may not be suitable for a propulsion drone's combustion chamber, but it could be useful as a sustainable replacement for plastic parts on drones. Thank you, and if you have any questions, you can always email me.